and then I think we'll just start. So today we'll kind of look over a bit of like an introduction to machine learning and artificial intelligence, or like AI, and more specifically kind of like image classification. Today it'll be kind of more like in preparation for the next time we meet, where we try to do more like of a demonstration, an actual example, something like that we can actually play around with. But kind of today we'll just kind of discuss and go over what exactly how all of this stuff kind of works. And so first, this is our schedule, just really quick, in case anyone's ever confused. We just go by the school's schedule or the district schedule. So like if there's a district holiday or something or spring break, then we won't meet. Otherwise, it would just be every other week. So today's the 20th. The next time we'll see is February 3rd, and then February. Oh wait, um, that those words there are incorrect. So just ignore that. I'll have those fixed. We'll fix those and then send the slides out later. But this is a quick table of contents. Essentially, first we want to start with some common examples, and then what are the differences between these two like terms, and then some of the definitions that are widely used. Then we'll start going to image classification, and we'll see if we can do the demonstration today, but it's probably unlikely. So we'll probably save the demonstration and the CNN portion for next time, and we'll try to do it together, or like we'll try to have everyone follow along. So here are some common examples of like what machine learning and AI could be used within. So with recommendation algorithms, for example, that's like when you're trying to watch a video, or like when you open social media or you open YouTube and they recommend you like videos, right? They kind of use a machine learning model to see based on your search history, your watch history, and try to like cater the videos to you so that you enjoy them more. And so that's a pretty common example. There's also like search engine algorithms. So like based on what you're searching for, like I could search a term and it might not be the exact definition that I'm looking for, but because the machine learning model is able to recognize that, it will show me what I still want to see. So for example, like if I were to search like walnut, it could check my location and it'll notice that, hey, this person's searching from walnut. So they're probably talking about the city, not about like the food, you know? It's little stuff like that. Um, there's GPS slash navigation. That's kind of straightforward. Like I don't think any of us here drive. I mean, maybe you do, but um, your car or like your phone navigation system, how the engine or how Google Maps, Apple Maps determines the best possible route for your car. That's also kind of like with machine learning, right? It takes in some of the data from other cars and the traffic at the time to determine, hey, this route is the best for you or whatever. And so that's another example. Then there's some more. There's face recognition, self-driving cars. Those are pretty self-explanatory. I think we're all kind of familiar with those, heard about them before. And like tagged photos. This one's a bit more interesting, and we'll be looking at tagged photos a bit more in depth. Um, but it's like the Google Photos. I think a lot of other like your phone's photos has the ability to like classify them for you. So like for example, your camera roll might have like 100,000 images, and it's able to categorize them into like different categories. Like it might have like pets, families, stuff like that. Um, maybe you've noticed that, maybe if you haven't, but the way that works is it's pretty simple. There's like a computer, right? It gets passed in the image. It looks at the image, does some magic, and it determines, hey, okay, this is an image of whatever, and it tags it for you. So then next time, right, you can go in your camera roll in your phone or your computer, whatever, and you can search for like your dog, and it'll be able to show you pictures of your dog, even though you don't necessarily, you yourself did not necessarily label them, but the computer is smart enough to do that for you. And so we'll kind of be looking at the photos a bit more. And so these two words, like machine learning, artificial intelligence, they're also kind of like commonly used together. I'm sure we've all kind of heard about them, but like there's some differences, key differences between these two ideas. And so first off, this isn't too important, so like don't get too worried about any of this. It's not essential, but it's just nice to know. Machine learning is kind of a branch of artificial intelligence, and it's the study of computer algorithms that allows computer programs to automatically improve through experience. That's like a very technical definition from CMU. It's like a really good college or whatever, a really, really good computer science place. But like a better, easier definition to understand is algorithms that can learn from data. The idea is you feed this computer a lot of data, and it takes in all of that data and it can learn from the data and be quote unquote smart. And artificial intelligence is more like the science and engineering of making computers behave in ways that until recently we thought required human intelligence. The important part is the human intelligence part. It's the idea that software can solve problems by itself. So there's no need to feed your computer data. Instead, you can just present it with data and it will be able to figure out the solutions by yourself. So like machine learning, you would probably feed you would first feed your computer images that have the answers to it. So I'll feed the computer a bunch of images of my dog and I'll tell them, hey, this is my dog. And it will know that it's my dog and keep on learning. And I'll see, okay, so this is the dog, and I'll keep on learning from that. But artificial intelligence is kind of like the opposite. You feed it a bunch of images of your dog, and the computer does not know it's your dog. And instead it has to try and guess that it's your dog. And every time it guesses it correctly, you kind of give it like a reward. And through these rewards, it starts to become smart and realize that, hey, I get rewards every time I guess this correctly as the dog. And so that's how the AI learns in comparison to the machine learning model. And so there's this website, it's called QuickDraw. It's by Google. Um, let's see. Uh, okay. The link's in the chat if you want to check it out yourself. But it's an AI experiment from Google. And what an AI experiment is, it's like has Google has this thing where they have like a bunch of collections or like quote unquote experiments. They're basically projects by like people who work for Google, or you can even make your own. You can submit if you have something really cool, you can submit it too. And it just showcases it. And you can check this out if you want. But QuickDraw is a neural network that can recognize drawings. So if I click Let's Draw, so it wants me to draw a map in under 20 seconds. And as I draw this map, the computer is going to try to guess what I'm drawing. And we'll see exactly what it's thinking. Um, so, so it says you just, um, and you can see in the bottom it shows what it's seeing. But like if I were to put so that's kind of how it works. Um, there's 5 more drawings, so I'll quickly go through the 5 drawings and talk about it a bit more. Essentially, the more you draw, uh, the more you draw, why is it not recognizing it's a cake? Okay, my drawing is not that good. I thought it was a good cake, but okay, I guess not. Okay, I think this is the last one. Okay, never mind. Okay, so you might notice that you thought like it's pretty quick, like the machine, like the computer recognizes the image extremely fast, except for the cake. I don't know what happened there. But the reason why it's so fast is because Google has a lot of data. So for example, if I were to click this map one right here, I can see that this is what I drew. And it thought my drawing looked kind of like a toaster, and you can see why it looked like a toaster because um, it, the computer's classification for a toaster kind of looks something like this, and my drawing is kind of outlined there. It kind of looks similar. Um, okay, I think that's better. And then it also thought it kind of looked like a keyboard, and you can see the similarities. Both have like that square feature to like I guess those are the keys and the spacebar, and mine kind of looks like that. But ultimately, it was a map, and then these are drawings by different people who have also played the game, and so those are all of the maps that there's like a lot of drawings. They're not all shown here, but the point is, by having this website and by having all of this data, right? Because me drawing this map, the computer is going to take this image and put it into its model and start learning again. And basically, we're teaching the AI, the machine learning model, by doing stuff like this. So, for example, like you notice when you need to verify that you're human, oftentimes it'll ask you to do like the captcha or like choose which pictures have like cars or like street lights, that stuff. On one hand, it kind of supposedly verifies if you're human, but on the other hand, what you're also doing is helping the machine learn by like right because you're indirectly telling them that hey, this is what a street light looks like, and you're helping train the machine learning model. And before we move on, did that was a rhinoceros and a dog and a bee. Okay. Anyways, so that's that. We'll look a bit more in depth on how it was able to recognize the drawings so quickly, but it's also largely in part because there are only so many options the machine has. So, for example, the machine can't just like come up with anything. You have to give it, for this case, um, for this specific scenario, the machine has like a list of maybe 1,000 different possible images or drawings it could be. And so that's why it's like really fast to determine what it actually is. And so that's quick draw. And then now we'll look at some machine learning terminology. So when someone mentions a label, that's a trait or like a category that we want to predict. So we're going to use this example of email and spam or not spam. So in your inbox, you'll notice that you have a spam folder. And inside your spam folder, there's probably a bunch of unread like messages that you haven't read because they're in your spam folder, right? They're like advertisements, actual scams, stuff like that. And you might wonder like, how does this computer know what to mark as spam or not spam? And so that's the example we're going to be looking at. So spam is a label and not spam is also a label. Those are the two things we want to be able to predict. We want to be able to know, hey, is this spam or is this not spam? And if features are like variables, they're like inputs. So a simple machine learning project might only have like one or two features, but like a more complicated one will have like millions of features. And so in our spam detector example, features could be like the words in your email, the address, the time, and whether like it contains certain phrases that are like red flags, right? If it contains this phrase, then okay, it's probably spam, and we'll want to give it the label as spam. And so features and labels, they kind of go together. The features help determine what the label is, and the features are what the machine learning model ultimately looks at to determine what the label should be. Then we have examples. So examples are like a combination of features and labels. It's a piece of data that we give to the machine. So this whole time I've been talking about like feeding the machine images. That would be an example. And there are two types of examples. There's labeled examples and unlabeled examples. The labeled examples have both your feature and the label. That's why they're called labeled. So for example, um, an email that the user explicitly marked, right? So they went out of their way to mark this as spam or mark it as not spam, right? If, for example, I dig through my spam folder and I find an email that's like important and I take it out of my spam folder, that would be a way to, that would be a labeled example because I, the user, have told the machine, hey, this is not spam. So what the machine can do is it can take that example, that that email all of the features from it, all of the information, and look at it and train the model and be like, okay, so this we know for sure is not spam. Why is it not spam? And it looks at the features and it determines why it's not spam, so it can mark it as not spam in the future. And then unlabeled examples are basically there's it's kind of self-explanatory. It's features without the label. So those would be newer emails that the user has not marked yet. So if a new email pops into my inbox, I haven't had the chance to look at it or mark it as spam or not spam, and that would be an unlabeled example. And we want our machine learning model, we want our computer to predict the label on these unlabeled examples. And that's like the ultimate goal for machine learning. And lastly, we have a model. So the model is kind of like an algorithm and it determines the relationship between these features and labels. It's like the computer, it does all of the work for you. And there's two phases of a model's life. The first phase is training, and that's where you feed the model labeled examples, and the model slowly learns from these examples and it gets smarter. And afterwards, after you've trained it enough, there's a second phase, which is inference. Um, it basically means where you actually apply the trained model to the unlabeled examples. So it's like you're actually testing your model for the first time. You can think of it as training, the training phase, and like the testing phase or the inference phase. And so now we're going to look at image classification. So this is the tagged photo section that I was talking about. So for example, how are you supposed to, given this image that's a cat, how is your machine, how is your computer supposed to determine and label that this is a cat? Um, it's kind of difficult because there's really not much you can work with. So we'll look at some of the difficulties first. The computer sees a bunch of numbers, right? Because ultimately we see this image and because we have a brain, right? And our brain does a lot of stuff and it can determine that, hey, that's a cat pretty easily. But the computer does not have that functionality, not yet at least. Instead, all it sees is a piece of data. It sees a large file. And in the file, it has a bunch of bits. And within these bits make up the each pixel of your image. So for example, our image might be a file with a bunch of data with numbers from 0 to 255 because those would be RGB values, right? Because red, green, blue goes from 0 to 255, and so you might have three numbers per pixel, and you would have a matrix, or you can think of it as a matrix or an array or like a grid, basically. A grid that is X by Y length of your image. So if your image is 800 pixels long by 600 pixels wide, then you might have an 800 by 600 by 3 grid of numbers. And from these numbers, you have to somehow take all of these arbitrary digits and turn it into a label of a cat. And the issue is if your camera, let's say your camera moves, if your camera starts off on this side and it moves to the other side, you still have the same image or you still have the same object in front of you in the image. It's still going to be a cat. That's not getting changed. However, all of your numbers get changed because your pixels have changed. And so therefore, it's like a whole different piece of data. However, it's still the same label, it's still the same cat. And so that's the first issue. And there are also similar issues with like illumination. As you can imagine, if the lighting is different, then your pixels might also be different. And it would totally change the data that the computer sees, even though it's the same cat. And then there's deformation. So some cats come in different shapes and sizes, but they are still considered cats. There's occlusion. They might be hiding. Like this one's kind of camouflage, not really, but kind of. This one's pretty well hidden, but you can still see, even though you can only see a tail and kind of a hump and whatever that is, you can still kind of infer that we can infer, at least as humans, that this is still a cat, even though it's really difficult for the computer to make that prediction. But with enough training in machine learning, it should be possible. And there's also background clutter. So this is more like camouflage. They're kind of blending into the background. Intra-class variation, that's a fancy way to say like there are different species of cats. There are different types of cats. There's baby cats or kittens, and they can still technically be classified as cats, or they could mess with your model. And let's say you don't want to classify kittens as cats, then you have to somehow figure out how to make sure that doesn't happen. And ultimately, How you would code your image classifier or your machine learning model is you'd have some sort of function, right? And your function takes in this image, and it needs to output this label. However, it's not like a very simple algorithm. It's not like a simple 2 plus 2, right? Or like a while loop or something where it's very structured. There's no obvious way to hard code this algorithm. There's no way for you to like check a bunch of like have a checklist run through it, and then based on this checklist, you determine a bunch of if statements. If this is true, if this is false, then return label is cat. It doesn't really work like that because of all the issues that we just kind of went over. You can try. So, for example, one of the more famous attempts has been the edge finding technique or edge detection. So, first, it takes your image and it turns it into black and white. It kind of filters some of the contours and ultimately creates this like map of your cat based on its lines. You can imagine it's not too difficult for your computer to turn this image into this image here, and then based on these lines and the outline, it can like find corners. So if three lines meet up in one edge, that could be a corner, that could be referencing an ear, and then so on. And then essentially it goes through and it has a bunch of if statements. But the two major issues with this approach is that one is not really accurate, as you can imagine, right? Like you would have a lot of if statements. There's probably some flaws in here, and it won't work 100% of the time. And also, the second issue, which is the bigger issue, is that it's not very um, redundant and you cannot replicate it either. For example, if you want to classify a dog, you would have to hard code everything all over again. And there's no easy way to turn your cat classifier into a dog classifier, which makes things kind of annoying. And so that's why this approach, like where you try to hard code the algorithm, does not really work for image classification. So instead, there's this video that we're gonna watch. It kind of goes over how the computers actually do it correctly. Um, I think you guys can hear it.
The internet wouldn't be the same without cats. From Garfield to Lil Bub and GitHub's Octocat, cats have become the internet's unofficial mascot, playing critical roles in some of the web's most viral content. But cats are unpredictable creatures. With millions upon millions of cat photos on the web, each containing very different shapes, textures, colors, poses, and backgrounds, how do we determine whether an image has a cat in it? Google Photos organizes all of your photos and makes them searchable. But how are cat photos identified when they are merely labeled with nondescript terms like Max? Image classification assigns text labels to images. But even with a huge number of training examples, computers cannot extrapolate enough meaningful information from raw pixels alone to easily identify a cat in a photo. We need to build models that can see pictures more like humans do. We can do that with a convolutional neural network. A convolutional filter is an n by n, for example, 3 by 3 grid of numbers that is applied to an image in different ways to generate a feature map, a map of all feature crosses or combinations in the image. Filters form a feature hierarchy. ConvNets use filters to build representations that become progressively easier to classify. From pixels to textures, from textures to shapes, and from shapes to objects. Training a small ConvNet, we can build a cat classifier that can identify cats with up to 80% accuracy using just 40 lines of code. Let's see the image classifier in action. Is there a cat in this photo? Definitely. How about this one? Most certainly not. A drawing of a cat is still identified as a cat. So is a cat relaxing on a bed. But a cat in a bunny-shaped cat bed? Not so much. However, even despite its high accuracy, the ConvNet has its limitations. As you can see, the human eye is still better than a machine at cat classification. Using a similar technique to the cat classifier, we can train models to classify dogs or even inanimate objects like handbags. To identify content labels in our training data, we leverage the same Google machine learning technology that powers Google Image Search and Google Photos, which can recognize over 27,000 different labels. ConvNets can also be trained to recognize more abstract concepts, such as whether a photo was taken on a smartphone or by a professional. These nets can be built on top of a pre-trained based network via a process called transfer learning, which makes it possible to train on far less data. Keep reading to learn more about convolutional neural.
All right, yeah, so that's pretty much it for the video. It kind of explains convolutional neural networks in a bit simpler terms, better than I can explain it at least. Um, that's also what we're going to be working on next time. We're going to be trying to, I do say trying because we'll see if it works out, but we'll be trying to create our own CNN or convolutional neural network, and we can try and classify some of our own images using our own webcams and stuff like that. So that's pretty much it. If anyone has any questions, now's the time. Otherwise, the meeting will probably be open for a bit longer, and we'll see everyone else in 2 weeks.